Okay, greetings from Lincoln, Nebraska, y'all. I'm here in Lincoln at a conference. I've got another lecture video for you, so let's get started. Hope the quiz went well, and here we go. Okay, so let's do this problem here. How many centimeters square is 13.5 inch square? In squares. And so recall there are 2.54 centimeters in an inch. So I want you to pause the video and find the solution for that. How many centimeter squares are in 13.5 inch squares? So maybe you did something like this. So 13.5 inch squared. And let's talk about my method. How is that a measurement? Well, it's basically the area that's 13.5 times as much as 1 inch square. And what is 1 inch square? Well, we can rewrite 1 inch square as how many centimeter squares? So here's an assumption that you might make, that if there's 1 inch is 2.54 centimeters, then 1 inch square is 2.54 centimeter squares. So did you do that? And is that right? So let's talk about that. So over here I'm showing an inch square. So suppose this is an inch square, but it's obviously much bigger. But suppose that this is 1 inch here. And this is 1 inch here. So what we're saying is, if we want to convert, we want to say what's equivalent to 1 inch square. We're saying how many centimeter squares fit in an inch square. So is it 2.54? So now down here I've got, this is a centimeter square. So that's a centimeter square right there. So we know that 2.54 centimeters, like along this edge, there'd be 2.54 centimeters that would make up that 1 inch. Does that mean there's 2.54 centimeter squares in 1 inch square? Well, so here's 2 centimeter square. And here's 2.54 centimeter square. So you see that even though there's 2.54 centimeters in an inch, there is not 2.54 centimeter squares in a 1 inch square. In fact, there is more, right? There's more. So I can zoom out here. So what's happening here? There's 2.54 centimeter squares along that edge, 2.54 centimeter squares along that edge. So how many centimeter squares is that? Well, it's actually not 2.54, but 2.54, hopefully you're thinking this by now, 2.54 squared. So if there's 2.54 centimeters in an inch, then there's 2.54 squared centimeter squares in 1 inch square. And you can see that in the picture right there. If this is an inch square, then there's 2.54 centimeters this way by 2.54 centimeters this way. So we need 2.54 times 2.54, or 2.54 squared. So this is our conversion factor to get from inches squared to centimeters squared. And so then we get 13.5 times 2.54, whatever that number turns out to be, will be how many centimeter squares is in 13.5 of these inch squares. So you got to be careful. This is a common mistake that students make. They assume that if there's 2.54 centimeters in an inch, then there's 2.54 centimeter squares in 1 inch square. That's not right. And this picture shows it, right? So you need 2.54 squared. The next property is volume. What is volume defined as? Volume is defined as the amount of 3D space occupied by an object. So area was the amount of two-dimensional space of a region or a flat region. And volume then is the amount of 3D space occupied by an object. Okay, so we're going to ask the same question we did before. What's going to be the standard reference for volume? So if we've got some space to fill up here, what's going to fill up the space? Okay, so since little squares filled up our two-dimensional region, what's going to fill up a three-dimensional region? Some of you might be thinking it, but little cubes. So since volume has 3 dimensions, like this dimension, and this dimension, it's distance and distance and distance 3 times instead of 2 times. So for instance, inches by inches by inches. And so our standard reference would be something like inches cubed. But again, instead of inches cubed, so I'm going to say no to that. And so instead we're going to call them what? Inch cubes. Cubes that are 1 inch by 1 inch by 1 inch. Okay, and so that's why raising something to the third power is called cubing it, because it's really the idea of creating a cube with that as the side length, in this case an inch, so inch cubes. So you can take any standard reference for distance, millimeters, centimeters, meters, miles, and you can make a cube out of it, and that can be a standard reference for volume. Inch, so inch cubes, centimeter cubes, millimeter cubes, etc. So what do the common formulas do? Just like the common formulas for area, what did they do? We said those formulas were a shortcut for counting squares. The formulas for volumes are counting cubes. So length times width times height, the volume of a rectangular box, it counts the number of cubes that fit inside the box. Okay, and for a sphere, it's the same thing as before. So we're going to use radius cubes. And how many radius cubes does it take to fill up a sphere? Well, this many radius cubes. This is about 4. So about 4, because divided by 3 and times pi, that's pretty close to 1. So we have about 4 radius cubes is the same volume as a sphere. Okay, and here's the volume of a cylinder, pi r squared h. All of these formulas, again, they count how many cubes would fit into that 3-dimensional shape. Okay, so here's a practice problem. A shoebox is 12 by 7 by 5 inches. What's the volume of the box in, so you can start with inches cubed. So start with, find the volume of the box in inch cubes, and then you're gonna convert that measurement into meters cubed, or meter cubes. Okay, pause the video and give that a try. Okay, so let's look at the solution to that. So it's 12 by 7 by 5 inches. So the volume of the box would be 12 times 7 times 5, and that would be 420 inch cubes. Okay, and so that's how many inch cubes would fit inside a shoebox. That's 12 by 7 by 5 inches. And so now the goal is we want to see how many meter cubes that is. So do you think one shoebox, do you think that's bigger or smaller than 1 meter cube? So a meter cube is pretty big. It's like a big box that you could actually crawl into. So a shoebox is going to be much smaller than a meter cube. So when we do this conversion, we're expecting a number smaller than 1, or a fraction of a meter cube is going to be equivalent to 420 inch cubes for a shoebox. Okay, so let's see how this works. So again, we're going to start by saying 420 inch cubes as a measurement is saying that it's a volume that's 420 times as big as 1 inch cube. And so thinking about getting to meter cubes, let's go from inch cubes to centimeter cubes. So hopefully you picked up on this. Is it going to be 2.54 centimeter cubes per inch cube? No, this is the same thing we learned before. This is a common mistake that students make, but since it's inch cubes, you need 2.54 cubed centimeter cubes would fill up 1 inch cube. Okay, so this number right here would give us centimeters cubed. And then that would be the same as 2.54 cubed times as big as 1 centimeter cube. And so now the question is, how many meter cubes are in 1 centimeter cube? Let's draw a picture here. So suppose this is a meter cube. This is 1 meter by 1 meter by 1 meter. And what's a centimeter? 1 centimeter is 1/100th of a meter. So centimeters is like if you drew a really small. So you drew a really small. So from there to there, it may be a centimeter. If 100 of those fill up 1 meter. So let's think about a centimeter cube then. A centimeter cube has a centimeter by a centimeter by a centimeter on all sides. So that's a centimeter cube. So are there 100 centimeter cubes in 1 meter cube? Definitely not, because there'd be 100 centimeter cubes just along this edge from here to here, since there's 100 centimeters in a meter. So this edge right there would have 100 centimeter cubes. This edge, just this edge right around there would have 100 centimeter cubes, and that edge right along there would have 100 centimeter cubes. So how many centimeter cubes in 1 meter cube? Well, you'd have 100 by 100 by 100. So it'd be 100 cubed centimeter cubes. It's actually a million. There's actually a million of these little centimeter cubes that would fill up a meter cube. So if you have 1 centimeter cube, that would be 1/1,000,000th of a meter cube. Because we just saw 100 centimeter cubes, 100 centimeter cubes, 100 centimeter cubes makes 100 cubed centimeter cubes that would fill up this meter cube. That's a million. So 1 centimeter cube, that right there is 1/1 millionth of that whole box, that whole meter cube. So now we're ready to do our calculation to get how many meter cubes is one shoebox. So we'll come up here and we'll do 420 times 2.54 cubed times 1 divided by 1,000,000. .0069. So just a small fraction of a meter cube would be one of those shoeboxes. So here's that meter cube. So just one small fraction would be that shoebox. Okay, so the volume problems that you'll have to do will be basically using the formulas to calculate volumes, remembering that whenever you use a formula for volume, what is it doing? It's counting up how many cubes would take up the same amount of space as the object that you're measuring, and then doing conversions. And remember, with volume conversions, you got to watch out. For instance, here again, 1 inch cube is 2.54 centimeters cubed, and 1 meter cube is 1,000,000 centimeter cubes, not 100. So it'd be 100 cubed centimeter cubes. So you just got to be careful on those conversions. Okay, so let's move on to another property here from volume. And we want to talk about the floating property. So there's a property of objects that causes an object to either float or sink. So let's just think about what that might be. So is it mass, meaning is it the amount of stuff? And if it were the amount of stuff, it were mass, then we might conclude that if something has less stuff, if it's less massive, it would float. And if it had more stuff, it would sink. Right? This would be the thinking, the rationale that would go behind saying mass is what causes something to float or sink. What do you think? Is this correct? Does the less mass something have give it more of a tendency to float versus the more mass it has gives it the tendency to sink? So let's think of an example. What about an aircraft carrier? That's a boat which planes fly off of. Is that pretty massive? Yeah, that's really, really massive, but it floats. And then what about a tiny pebble? Well, a tiny pebble is not very massive at all, but what does it do? It sinks. Another example would be a golf ball and a surfboard. Which one has more mass? Well, a surfboard has more mass than a golf ball, but golf balls sink and surfboards float. So this idea that mass is what causes things to float or sink isn't right, because really massive things or not very massive things could both sink or both float. Depends on what it is. So another possibility we could think about, that's the reason things float or sink, is volume. And what would our reasoning be there? The reasoning would be that if it's smaller, it would float, and if it was bigger, it would sink. What about this? Does this fit the bill here? Well, no, because you could just look at the same example of a golf ball and a surfboard. The big thing, the thing that took up more space, the surfboard, it floats. And a golf ball, which is smaller, it sinks. So it's not mass that causes something to float, or it causes something to sink. It's not volume that causes something to sink. So what is it? So instead, the property is actually how compact the actual stuff is. Is it really compact together, or are the molecules kind of spread out? Is the material inside spread out? Like surfboard is foam, right? And so the molecules in foam, think of that as like spread out, whereas like a rock or a pebble that has very compact, the matter is very compact. And so what's the key word here? Does anyone know the key word we're talking about when we talk about the compactness or spread of the molecules in the material? So maybe some of you are thinking or saying density. Okay, so density is not fundamental because density is based on mass and volume, and we know volume is based on distance. So if you take distance cubed, that's volume, and you combine it with mass in this relationship of mass per volume, you get density. All right, so let's explore more about density here. Oops. So any mass per volume unit would be a density unit. For instance, grams per centimeter cubed, grams per milliliter. So milliliter is a liquid volume, but that would be density. Or kilograms per meter cube. These are all examples of density standard references. Okay, so here's a density practice. Here is a game you guys can play. You can make teams of 2 or 3, and within your teams decide of each of these pairs of objects which one is a higher density. Again, remember what density is. Density is the spread or the compactness of the material in question. Okay, so here they are. For instance, a sponge or a rock. Don't say yet. You're going to do these in your teams. So just hold your tongue for a sec. A row of staples or a single staple. A bag of grass or a bag of leaves. A 2x4, that's a piece of wood, okay, or a wood splinter. That's a 2x4 is something like this. Looks like this. It's like a standard piece of wood you make a wall out of, a wall frame. So that's a 2x4, something like that. Or a wood splinter, a chocolate bar or a gold bar, helium or air, an ice sculpture, or a drop of water. Okay, so make your teams of 2 or 3 and decide for each of these pairs of things. So there's 1, 2, 3, 7 of them. For each of these pairs, you're deciding which in the pair has a higher density. So pause the video and take 5 minutes to see what you think in your pairs or your groups of 3. So pause the video. Okay, so how do we do? So what has higher density, a sponge or a rock? So hopefully you said a rock. Okay, what has higher density, a row of staples or a single staple? Okay, so did some of you say a row of staples is a higher density? Okay, how does a row of staples compare to a single staple? Isn't it just more of the same material? So it has a bigger volume, it has a bigger mass. Remember we said mass and volume aren't the determining thing. What's the determining thing for density? Density is the spread of the material or compactness of the material. So it's a property of the material. So which one would have higher densities, a row of staples or a single staple? Well, it's actually a trick question, and if any of the teams said the same, congratulations. These two have the same density because they're the same material. They have the molecules in the staple. It's like aluminum. The molecules in a row of staples have the same compactness as in a single staple. Okay, what about a bag of grass or a bag of leaves? Well, so we're asking which is more compact? Grass in a bag would be more compact. Okay, what about a 2x4 or a wood splinter? All right, do you want to change your answer after looking at number 2? Same. Again, yes, it's a bigger volume of wood. Yes, it's more mass of wood, but it's the same material. They're both wood, so it's the same density. Chocolate bar or gold bar? Gold is very dense. Gold is a very dense metal. Chocolate bar, chocolate's not so dense. Okay, what about helium or air? So you know what happens in a helium balloon? It floats up. So what causes something to float? The density. So if helium's floating on air, then its density must be less. So air is actually more dense than helium. Okay, what about an ice sculpture versus a drop of water? Okay, so we don't want to get fooled by the fact that an ice sculpture could be a big, massive thing, and a drop of water could be a little tiny thing. So we want to think about what happens when you put ice in a glass of water. What does the ice do? It floats. So then which one of these is more density? Ice, or is more dense? Ice or liquid water? If ice floats in liquid water, then liquid water is more dense. Okay? So what happens when water freezes? It actually expands a little bit, so it becomes less dense than liquid water. So did any teams get all of these right? Or maybe did you get 6 right, or did you get 5 right? That would be really, really good. And if any team got all 7 correct before I started explaining them, I'll give you a prize. Okay? Next week. Okay, have a good weekend. I hope you enjoyed your first week of Upward Bound and physics, and get some rest this weekend. We'll see you ready to go on Monday.